Huh? 1.5, no? 90 minutes.
Okay, I think that also other people, other students will arrive. We have to start and not to delay the schedule. So the first lecture today is Gustavo Burdman, and he will continue his set of lectures on standard model.
Thank you, Enrico. Is this on, right? You can hear me? Okay. So we start the lecture today with the spontaneous symmetry breaking of a gauge symmetry, okay, or gauge theory. So our theory now is going to have a covariant derivative we're still going to have the same potential as yesterday. Now we have a kinetic term for this gauge field. And this is going to be a U1 gauge theory. So for the global symmetry, we used this potential yesterday. I'm already going to consider that the quadratic term on the fields is going to be negative. The coefficient of the quadratic term is negative in the potential. And then I have this quartic term. So the potential is the same, right? And so the minimum of the potential is the same. And so the question is, what happens when the symmetry that is spontaneously broken is not a global symmetry, but a local or gauged symmetry, where, of course, what we mean by a gauge symmetry, U1 local transformation is that phi of x goes to e to the I. Now I have this alpha depending on space-time coordinates. But now, the covariant derivative, as you well probably know, is defined as the normal derivative minus I times, I'm going to call this coupling. Doesn't matter which sign I put in here. I'm going to put a plus here. This coupling E. So this is the covariant derivative on the scalar field phi, which means that the scalar field phi transforms non-trivially under the local symmetry, but also a vector field that I need to introduce in the covariant derivative will transform in order for the Lagrangian to be, so you know the story, I have to put in this here, the mu alpha of x, okay? So this is the local U1 symmetry of this Lagrangian. For the potential is the same as for the U1 global symmetry, since there are no derivatives in the potential. That's basically what we mean by the potential. But then in the kinetic term, and also here, I need to tell you that F mu nu, of course, as you probably know, is defined to be d mu a nu minus d nu a mu, a totally, it's a standard U1 gauge theory, just like QED. Let's say this is scalar QED. But now it's spontaneously broken by this non-trivial potential that has this minimum, right? The minimum of the potential, which is pretty much the same as the global case. So the minimum of the potential, if you remember, from yesterday, the minimum of the potential, which now I'm going to write it as this vacuum expectation value of of phi star phi, this is m square divided by lambda, which I called v square. Okay? Very good. So this is exactly the same. Everything is the same. We had our phi of x now written as v plus eta of x plus I xi of x. And these real scalar fields now are, the actual fluctuations about the vacuum. So these are the fluctuations. If you remember, if this is the potential, now these are the fluctuations about this minimum. This is phi star phi minimum, which I call v square. So about this non-trivial place, I'll have essentially my fluctuations eta and psi as particles being produced, excitations about this vacuum. Very good. So what happened in this case now, that is new, is that the kinetic term for the scalar field now also will have new terms coming from the covariant derivatives, okay? So now in the covariant derivatives, okay, let me just write the kinetic term. This is going to be, when I do all the replacements, we're going to have the kinetic term for the eta, the kinetic term for the xi, okay, this xi here, okay? But now, here we have this new term, this quadratic in the gauge boson field that looks like a mass because it has, well, whatever it is, it has the correct units of energy squared, so it looks like a mass. It looks like a mass equal to E times V, okay? But there is another quadratic term in the fields. There are a bunch of other terms, but there is another quadratic term in the field, which is this one, E times V times A mu d mu psi. And then there are other terms, but these are the quadratic terms. So if I'm worried about the masses, the spectrum of the theory, of course, there are quadratic terms in the potential for eta. If you remember, eta has a mass. In this potential gives a mass to eta and no mass to psi. This is still the same story because these quadratic terms come from the potential. But now, from the kinetic term of the scalar field comes a quadratic term for the new vector boson, okay? And that looks like a mass. But there is also this weird quadratic term that is kind of a mixing between the gauge boson and the scalar field, which is massless. If you remember, this theory has an eta mass of square root of 2 times m, the parameter m, which is the quadratic parameter. And then we have the mass of the xi equal to 0. So this is the Nabu-Goldstone boson. This is the massive excitation, the Higgs, if you want to call it. And now it turns out that the Nabu-Goldstone boson is mixing with this gauge boson. And then there is a mass term for the gauge boson. Okay. What does this mixing mean? Let's say that I have to derive the Feynman rule of this two-point function term. It's a term, it would be a weird term because it's a two-point function like this. There is a gauge boson, and then all of a sudden, it becomes a scalar. That's the Feynman rule for this thing, right? So there is a mu here. It better be some index here which comes from the derivative, right? So if this is the momentum, I don't know, k mu of this line, it has a unique momentum, it's a two-point function, then what would be the momentum if I go to derive this in momentum space, this Feynman rule in momentum space? What it would be in this Feynman rule, okay? Well, this Feynman rule would look like this, would look like, there is an I, if you want, for these conventions of the Feynman rules. There is EV, this is the amplitude. And then there is a momentum that comes down from the momentum expansion of this field, right? And this momentum is K mu, depending on which way it's going. I'm going to, write K mu. And this is contracted with the polarization in momentum space, is the polarization of the vector field, right? And so when I do this, so of course, this is a Feynman rule, a new Feynman rule for the theory. You have to, work in this situation where, you have this weird Feynman rule. We can get rid of this in a minute, but at the moment, I want you to ask the following question. There is a mass term for a gauge boson, which was massless to begin with. That's the theory for a massless gauge boson, right? There's no mass term here because it would be gauge non-invariant, right? But now there is a mass term here, and then there is this mixing of the momentum with eventually the polarization of the field, right? So what kind of polarization of a spin 1 particle can mix with its own momentum? Yeah, there's a name for it, or any name in any language. Which polarization is it? It's the longitudinal polarization. It's the polarization that has, so if you have a polarization, I put the mu here, and then the momentum K mu, right? In order to mix these two polarizations, if this was a transverse polarization, what is a transverse polarization? So let's say that the momentum is in direction Z. Oh, this is Z times, some number. And so the longitudinal, so this momentum is in this direction. Now, the transverse polarizations typically are vectors like this, 0, I don't know, epsilon 1, or epsilon x, epsilon y, 0. That's a transverse type of polarization, right? There is no component in the longitudinal, no time component, right? That's what is the massless gauge boson, and also, if you're talking about electromagnetism, is the same. So what this means is that in order for this to be non-zero, in order for this mixing to exist, since K mu has to have, K mu is essentially has to have this component K in the Z direction, right? Then, and so the spatial components are 0 here for K. And so essentially for this to be non-zero, it turns out that the gauge boson polarization cannot be transverse. It has to have a longitudinal component. And this is what this is telling us. It's telling us that if I got a mass, I also got a longitudinal component for the gauge boson. So this implies that there is a longitudinal component polarization as a function of K. And this, of course, has to be like this. The absolute value of K has to be also the 0 component, 0, 0, the absolute value of K, because, of course, and so it has to be proportional to the longitudinal, and so it has, maybe you should do it like this, okay? It's a unit vector. So it has to have a longitudinal component here, okay? So the fact that there is a longitudinal component already is consistent with me having a mass, and I could stop there. So A mu acquires a mass, which is, M A is equal to E times V, but it also acquires a longitudinal component. Polarization. Which is consistent with acquiring a mass. If you have a massive a spin 1 particle, it has to have 2 transverse polarizations and a longitudinal polarization. If it's massless, then nothing, just the transverse. Now, it's a little annoying to have to actually work with this kind of a situation where your gauge boson disappears into a scalar particle, but that's fine. You can just do calculations, and in fact, you know, people do. And in fact, it is advantageous, for example, to ask the following question. The fact that I have a mass, is this a violation of gauge invariant? Because you would say, well, gauge invariant is not explicit here. It was here, and what did I do to go from here to here? Well, I did a change of variables on the scalar field. That's all I did. Change of variables that allow me to expand about the correct quanta, scalar quanta about the vacuum, but that's still a change of variables, right? So I didn't do anything to the Lagrangian. I need to add a term that is not gauge invariant. So my theory should still be gauge invariant, despite me having a mass term. How do I convince myself of that? Well, one way to convince yourself of that is to make sure that the word identities of the theory, which are one way of checking gauge invariant, are still correct. And for example, in this case, I want to know if the two-point function of the gauge boson is still transverse, right? So is the A mu two-point function still transverse? Which means transverse, which means that it's still respecting the word identities and therefore gauge invariance. And the way to see this is to add to the two-point function the two new terms. There is a mass term, so there are two new terms in the two-point function for the gauge boson. So I'm going to call this delta pi mu nu, okay? So the two-point function was like this. Now I have a mass term that I'm going to signify like this, okay? And now I have some other term. So this is a mass term, so mu and nu with the g mu and nu with the g mu nu in the middle, of course. This is the two-point function. But then we have this, which is a mass term. And then we have this other contribution, which is very important not to forget. This is also a contribution to the two-point function, okay? This is the contribution of the Nabu-Goldstone boson pole. It's a pole because, you know, it's a propagator here, okay? So when I add these two contributions, it turns out when I add these two contributions, it turns out that I get the following. I here. The first one is just the mass of the gauge boson times g mu nu. So this one is just this mass term here, right? Times g mu nu because I have mu and nu. Very good. What about the second term? Well, the second term is also what is this vertex here? This vertex here is I have an E and a V. Okay, this is the mass of the gauge boson too. Okay, so I have the mass of the gauge boson, 1/power of it. Then I have the momentum, right? The momentum. Let's say if I'm going that way with a minus sign, minus I k mu. And now I have the propagator of this Nabu-Goldstone boson. And remember, it's a Nabu-Goldstone boson, so its mass is equal to 0. I'm going to write it as I divided by k squared. And then on the other vertex, I have the same thing, MA times, now I have plus I, okay, very good, K nu, okay, which when I add it up gives me MA square times G mu nu minus K nu divided by K square. So now the two new contributions that come from breaking spontaneously the symmetry are like this, and these are transverse. Transverse meaning if I multiply this by, for example, K mu or K nu, I get 0. And that's, the simple test of transversality of a two-point function for the word identities. So crucial in the fact that this is transverse is the fact that the scalar in this second term is massless, is the Nambu-Goldstone boson. If this was not massless, this was not transverse. This is not transverse, okay? Which means that the fact that the spontaneous symmetry breakdown over gauge symmetry still respects the gauge symmetry, it is absolutely tied to the fact that there are massless scalars due to the fact that I broke spontaneously a continuous symmetry, and Goldstone told me that there are massless particles. These massless particles mix with the gauge boson, and in the end, I get still a transverse gauge respecting two-point function. Okay. Now, some things you can do is you may not want to have these two-point functions around. And of course, the mixing is the mixing of a gauge boson with a scalar, but you can always change the gauge. You can change the gauge, right? And in particular, you can go to a gauge where you get rid of this mixing, right? Why? I mean, I don't want to have to draw the little dots every time I have to have the wavy line. I don't know. And so you can do a gauge transformation and go to a gauge, which is called unitary gauge. It cancels the mixing. To cancel the mixing, you go to the unitary gauge. So you go to A mu going to some other A mu prime. And this is just like any gauge transformation, but in particular, in this case, I have to choose that alpha is equal to minus, actually, remember this was, it's too far from, it was minus 1 over E alpha. Now I'm going to choose alpha of x equal to minus 1 over V times psi of x. It is the fact that now the gauge parameter, which is arbitrary for a gauge transformation, depends on x, that allows me to choose it equal to or proportional to the Nambu-Goldstone boson field, right? Otherwise, if this was a constant, I couldn't do that. And so you do this, 1 over EV d mu, I'm sorry. Yeah, d mu of psi of x. You put this back in the Lagrangian, and there you see what happens. And this is what happens. In particular, the only place that I need to put this back is in the kinetic term of the scalar field, because it's the only place where there are gauge bosons. So I put this back in here, for example, right? And then it turns out that this is going to be 1/2 of d mu eta d mu eta. Then I'm going to have plus 1/2 e square v square a mu, and that's it. Of course, there could be interaction terms, but they involve maybe eta, but they don't involve psi. Psi of x disappears from the theory. I don't know if it has so many double letters. I think it's just one here. Disappears. It's gone. You can do the calculations, but I'm going to show you a way to do it that is pretty obvious in a minute, right? Now, it turns out that if I do a gauge transformation, the gauge transformation that gets rid of the mixing term, it turns out that not only I get rid of the mixing term, I get rid of the kinetic terms of psi, which are the only terms psi has because it has no mass. And you can see how this happens because a mu will have something that looks like a kinetic term. There will be a cancellation of the EV, the denominator, numerator. You can see that how it happens, but you have to work through, and it looks like a little bit of a miracle. Now, it's not really a miracle. It's always going to happen. And the way we can see this is by going to the representation of the scalar field phi, that instead of being real part, imaginary part, is that exponential representation we saw yesterday for the global symmetry, but now for the local symmetry. And this is going to be like, oh, obviously. Okay? And the way to do it, is then, if I tell you now that I don't know why I have this. There was nothing in this page that I actually had to write. I don't know. I'm carrying the page, and none of it is the page that I needed. Anyway, I think I'm going to remember. Oh, okay, probably here. Okay, so now if I do this representation, which was e to the I pi of x. Remember, we had an f here that it was equal to v, I think. Okay, and then we had v plus sigma of x. Okay. So this theory, if I replace here, will have the same type of Lagrangian as this. Here would be sigma, here would be pi, it's the same thing. Pi would be massless. Why is it that pi is massless? So why is it that pi is massless in this theory with this representation? Where are the masses coming from for the scalar fields? From the potential. The potential depends on phi star phi. So is it going to be a pi in the potential? No, no pi in the potential. So if there is no pi in the potential, there is no mass for pi. Okay? So clearly, one thing you already know from yesterday is that then pi is 0. Okay? And you can bet that m sigma is going to be square root of 2 times m. That's for sure, but you have to work on it. But m pi equals to 0 is pretty obvious. The second thing that now we can do in this case, which is the U1 gauge theory as opposed to the U1 global symmetry, is that I can now do a gauge transformation to eliminate pi. What's the gauge transformation to eliminate pi? This is the simple that eliminates pi of x as a field. The gauge transformation, remember, for phi was phi prime of x equals to e to the I alpha of x times phi of x. So what do I have to choose alpha in my new field to eliminate pi? this is minus 1 over v times pi, which is that gauge transformation, the same one we had over there, okay? So pretty obvious, I should have started with this parametrization. So if alpha of x is equal to minus 1 over v times pi of x, that implies no pi in the theory, no pi of x in the theory, gone, okay? This gauge is the unitary gauge, okay? And in this unitary gauge, I have the massive gauge boson. I don't need to worry about the longitudinal polarization mixing, but it is important to realize that the longitudinal polarization is, in fact, coming from that mixing term. Now, in this gauge, since there is no pi, you say, well, I still have a longitudinal polarization for the gauge boson because the gauge boson is still massive, right? I still have the mass term. So what is it? Well, there is a theorem that proves that it is, in fact, the Nambu-Goldstone boson, right? It's called the equivalence theorem, and it's not easy to prove. But that's why people, when they talk about the Higgs mechanism like this, they say, well, that the longitudinal polarization ate the Nambu-Goldstone boson, or something like that. I mean, it looks like the children's book version of the Higgs mechanism. And then, you know, the gauge boson ate. Okay, never mind. So that's really the end of the story, okay? That's what happens in this mechanism, which was first invented by Philip Anderson in 1958. I know you haven't heard of Philip Anderson, maybe. You talk about the Higgs mechanism, is the Anderson-Higgs mechanism, or the Anderson-Braut-Englert-Guralnik Higgs mechanism, but it's easier to call it the Higgs mechanism, okay? Anyway, so now questions about this before we move on to non-abelian symmetries, which is going to be very fast. All right, good. Now we're going to move to a symmetry that is non-abelian. First, I'm going to go with a very quickly with the non-abelian global symmetries. And so I'm going to have to put little indices and stuff like that for the non-abelian symmetries. This is a global symmetry, so now I don't have to worry about the covariant derivative. So d mu phi, d mu phi. Well, this didn't look very nice. There is no gauge boson for now, okay? The potential is the same shape, the same expression for the potential. But now, the field, the global symmetry transformation, it has this structure, alpha A times TA times phi of x, where, of course, TA are the generators of the non-abelian global symmetric group. G is UN or SON or whichever is your favorite global symmetry, okay? And these are real constants, alpha A, TA, okay? Obviously, phi has little indices. We've seen this. But now I want to know what do I mean by the vacuum? Remember the story. How do I know if the symmetry is spontaneously broken? Well, symmetry is spontaneously broken if the ground state is not annihilated by whom? So let's talk about this now. It's not invariant, let's say. It's not invariant under the symmetry. So if the Lagrangian is invariant under this global symmetry transformation, just by looking at it, this is the transformation, it's global, so I don't need any covariant derivative. But what happens if the vacuum of the ground state of the theory is not? I know that here I have that potential, if you remember, right? Minus 1/2 phi star phi, m squared phi star phi is the same potential, right? Which means that there is a minimum of the potential, which is v squared or whatever, m squared over lambda, is not trivial. I want to know if that is invariant under the symmetry. So how do I do that? Well, I say, well, this is the vacuum expectation value of the field, the minimum of the potential. So first of all, what is the ground state? The ground state of the theory is defined by the minimum of phi, or phi star, it doesn't matter. So this is the minimum, which is the expectation value of phi in the ground state, okay? That's what defines the ground state, okay? So I'm going to call this the expectation value of phi in the ground state. That's that's what I want to know if it transforms under the symmetry in a way that is invariant, and that's how we know if the ground state is invariant or not. However, now things are a little bit more complicated because I have these generators in the exponent. It's not just alpha times the identity. So the transformation of the ground state is like this. Right? Which I can expand as 1 plus I alpha A T A blah, 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 applied to the vacuum. So if the action of the generator on the vacuum is such that this is 0, then you say the vacuum is invariant. If all the generators acting on phi are 0, remember that phi, when I mean by phi, I'm going to do an example, but phi is not a trivial object. It has internal components. So if this is ij, this is j. So the action of these matrices on the vacuum is the action on this little vector, if you want to call it, this multiplet of g, which is the vacuum, right? If the field is a multiplet, then the vacuum is a constant, but it has little entries in this multiplet. So it's not trivial what the action of the generator on phi is, okay? It depends on what these matrices are, depends on the group, and depends on the vacuum that I chose. Where do I put V inside this phi, right? And so this may happen. So this means that there is an invariance, okay? But what if this doesn't happen? Then there is a spontaneous symmetry breaking. Well, there could be values of this index A for which this happens, and values of this index A for which this other thing happened. So now finally answering Lorenzo's question from yesterday. Good morning. So So now there are going to be generators for which the vacuum is annihilated, and other generators for which the vacuum is not annihilated. So how do I decide what happens to the symmetry? And so what I'm going to have to decide is that there are generators that spontaneously break the symmetry and other ones that don't. And that means that the symmetry is broken partially, if this is the case, and not totally. So I have to check. Okay? So typically, you change the name of the generators. These ones are called broken generators, and these ones are called unbroken generators, something like that, okay? Because there are directions in group space. The generators are a space in group space. There are directions that annihilate the vacuum, and there are directions that do not annihilate the vacuum. So let's just give an example. Let me give one example. That you're going to have to work in the details, but it's pretty obvious, okay? Suppose that the group is SU3. And I'm not going to go through the whole thing. It's going to be an exercise for you to finish this. But suppose, because we're going to do it for the gauge theory too, and you're going to do that. So suppose that I have SU3, right? In SU3, and I have this, the field in SU3, in the fundamental representation of SU3 are triplets. They have 3 components, and I'm going to put it as a little column vector, okay? And so this is a triplet of SU3. It's denoted as 3 of SU3, but it's just notation. In any case, what really I care about is the following. I'm going to choose the vacuum of this as this, 0, 0, V. So that's going to be the vacuum that I chose. Why? I don't know. I can choose the vacuum. We'll talk about this in a minute, But I chose this. Now I have the generators of SU3. There are 8 generators, n squared minus 1, right? 8 generators of SU3. The first 3 generators of SU3 are very easy to write, and I'm going to choose to write them in the following way. The Pauli matrices divided by 2, I is equal to 1, 2, 3. And then everything else is 0 everywhere, okay? So 3 by 3 matrices, but the only non-zero things are here, the Pauli matrices. This is one way to see that SU2 is a subgroup of, you can embed SU2 inside SU3, okay? So these are the Pauli matrices, if you remember, and if you don't, you should always know, they're always going to be handy. And we're going to use it a lot. All right, so there are traceless, blah, blah, blah. Now, there are other, for example, T4 is like this, 1, 1, 0, 0, 0, okay? T5, I'm not going to do the whole thing, but you can see how this is going, okay? So you're basically, this T5, this T6, this T8. This T8 is the only one I'm going to write here. Blah, 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 blah. 1 over the square root of 3. It doesn't matter. It's a diagonal generator. 1 minus 2, okay? The point is, which of all these generators will annihilate this vacuum? Well, clearly, T1, 2, 3 annihilate the vacuum. Whereas, for example, T4 clearly does not. In other words, I mean like this. Ti with 1, 2, 3 times this is going to give me this. I mean, like 0, really, nothing. All the other generators are not going to do that. They do not annihilate the vacuum. The question I'm asking you now is, how many massless Nambu-Goldstone bosons shall I have here? Are you raising your hand or saying 5? Okay. This could be, I don't know. All right, 5. 5, because I have 5 broken generators, 5 directions in group space that are not annihilating the vacuum. And for each one of those, I'll have a massless Nambu-Goldstone boson, okay? We're saying, the way we say this is that this vacuum breaks SU3 into SU2. In other words, the fact that SU2 still annihilates the vacuum means it was not, this subgroup of SU3 was not spontaneously broken, because it's the other generators that are not SU2 generators that are breaking the symmetry spontaneously. And that's called the coset space, okay? These generators here are the coset space, which is a fancy way, if you want to impress people, of saying the generators of SU3 that are not the ones in SU2. So just the coset space, okay? Good. I mean, there's more to it, but this is math, okay? Very good. Okay. Now, so you, what would have happened? This is a question for you to exercise. Suppose that I did SU2 instead of SU3. If I did SU2 instead of SU3, this is the exercise. What happens if I choose this vacuum? Exercise. Okay? So if I choose this vacuum, how many Nambu-Goldstone bosons I'll get? That's an exercise, okay? Anyway, now let's assume now, any questions about this? Okay, yes, or 5, no, it's a question. Yeah, well, that's of course. You can ask me, what if I put the V up here, right? Now it turns out that there are going to be 3 generators that are going to annihilate the group, but it's not going to be that obvious for me to tell you which ones are. You have to work on it. The way to prove this is to actually do a similarity transformation on the generators, apply it also to the multiplets, and see that when I do the transformation to another basis, I get the same answer. Some of them are, which ones are 0, which ones are not 0. But this is the one way of doing it that is pretty obvious. It's not going to depend on my choice of basis of generators or where I put the V. It's going to depend, for example, if I put 2 Vs, then I'm going to get a different result, right? If I have 2 Vs, then that's going to be different, right? Yes. Okay. Yes. You're talking about the basis for the generators or the representation of the phi? No, this is physics, right? I have phi in the fundamental representation, but I could have had it in the adjoint representation. This is physics. This is not just a mathematical choice, right? If I'm trying to represent some field, some scalar field in the adjoint representation, this whole thing is different, okay? So that's physics. The fact that, for example, the Higgs is a doublet the fundamental representation of SU2 are not a triplet, it just reflects the fact that if it was a triplet, all our experiments will tell us that it's wrong. So it's a choice.
There should be also a factor U1.
I'm sorry?
There should also be a factor U1, which is probably generated by...
So yeah, the 8 generator, yes, sure. I mean, the SU3 contains SU2 and U1.
But also because when you break with the fundamental, you always break to a maximal subgroup.
Right.
The maximal subgroup is SU2 plus U1. There is a
Oh, no.
theory. If you break a simple group with a fundamental, then you go to a maximal subgroup.
But you're saying that that this generator annihilates.
There should be a U1 next to it.
Okay, we can think about this. All right. Any more questions? All right. Now let's suppose that I'm going to do the same for a gauge, not abelian theory. Gauge and abelian theory, or gauge. So this is the covariant derivative. I need to put this carefully like this. Let me rewrite it. So this is a gauge. This is a covariant derivative. Potential is the same. Now I have here X. I still have the ground state. And now we're going to do the same thing we did for the U1. And then the question is, what's going to happen when I have now, knowing what we know, what's going to happen when I have this non-zero expectation value of the field in the minimum, and I do the change of variables that I need to do. So what's going to happen to the gauge field? And of course, you know the gauge field also is going to acquire mass, but now it's more complicated. Okay? So how is it going to work out? So once again, I want to write down, I'm going to do this quick, so I want to write down the kinetic term of the scalar field. Now the scalar field is just the same as in the global case, but now we have this, okay? What is changing now is that I have to have here, maybe I should, the potential is the same, but now I have here a kinetic term for the gauge fields, minus 1/4 F mu nu A, F A mu nu, so non-abelian gauge fields. The covariant derivatives, of course, are d mu minus I sum coupling G, A mu of X, A with the generators TA, okay, acting on phi. And and I want to know what happens to this term. And so this term now is going to be like this. It's going to have I'm going to stay in this in this case of phi, I'm going to stay with phi, okay? But I'm going to obtain sort of a, there will be a covariant derivative that it will first term, I'll have a mass term here, a kinetic term. But then I'm going to have a term that is just like the mass term before. There was A mu, A B mu. And then we're going to have, there's a minus I T A with the phi. And then there is a T, I T, did I put this a minus? So this is a plus and this is a minus, but it doesn't really matter. T B with the phi. So this would be like a quadratic term for the gauge boson. And of course, there's going to be a mixing term. A mu times, there are two terms. So there's going to be like a real, okay, there is a TA phi. There are two terms that are going to give you the I'm just changing notation as I go because I don't want to go through some other definition, okay? But maybe I should go to that another definition. Let's assume for a second that I'm going to change from this representation of the field where I have some field phi 1 and some field phi 2 and some field phi n, okay, in this representation, where each of them is a complex scalar field, right? I'm going to go to a representation of the group that is real, in which I'm going to take the real part and the imaginary part in different places here. So this, from this, I'm going to go to, the real part of phi 1, the imaginary part of phi 1, the real part of phi 2, etc., and then the imaginary part of phi n. So this is like a 2n real representation of the complex n multiplet, okay? So if I do that, then I can replace, so then the generators in this representation must be totally imaginary, and then I can replace them by real representations. So these are real, and these are imaginary, completely imaginary. This is annoying, but it's necessary because in this way, for example, I write the covariant derivative as this real object, and this is the real component, the imaginary part or the real part of each of the two n fields. So here I have these two n fields. And the reason why this is advantageous is because the fields that are going to be massless or not massless are, acquire VEPs or not, are these in the real representations, the real scalar fields. So this is the I's, right? And this is the real generator TB, okay? And here the same thing, so it doesn't matter. So it's T8 and phi, and it's the component I of this, and then d mu of phi I. So this is the mixing term. This is the so this is the mixing term. This is the what it would be the would-be mass term. Okay. And now the question is, if I now take the vacuum expectation value of the scalar fields, some of them will acquire vacuum expectation value, right? So I will put this some v somewhere in here, right? And now the question is, if I now ask the question, which of the gauge bosons will be massive and which of the gauge bosons will not be massive, that question would have to do with the action of these generators on the vacuum phi. So if the generators acting on the vacuum phi break spontaneously the symmetry, so if they don't annihilate a vacuum, so if I replace the field by the vacuum now, right? If I put the field and replace by the vacuum, so I expand around the vacuum, right? So I can have a mass for the gauge bosons, a mass, the mass, which is essentially the following, is equal to G square times the action of this generator A on the minimum of the potential component I, where the field, this is the component I, goes, I here goes from 1 to 2n. They're all scalar fields, real scalar fields. And now this times TB phi 0 component I. So now the question is, if a generator annihilates the vacuum, that means that it doesn't break spontaneously the symmetry of the global case, remember? And here it means that it doesn't give a mass to a gauge boson. Okay? Whereas if the generator annihilates, does not annihilate the vacuum, then it will give me a mass for the gauge boson. Okay? Now, this is tied to a very generic Goldstone theorem, but essentially generators, so when I have this different from 0, implies gauge boson masses. Okay? So let's do an example to see this at work. Okay? So the example, of course, has to be SU2. Okay? And I'm sorry I'm going so slow, but maybe I should skip the details and just give SU2 and go to the standard model directly. Okay? Certainly, it will be easier with the slides, but so for SU2, gauge symmetry, I'm going to take the following situation. Yes? Is a question? No? No, okay. So for SU2, I'm going to have our usual potential, the SU2 kinetic term. And now I'm going to say, what's going to be the vacuum, okay? The generators of SU2, of course, we know what they are. And the vacuum that I'm going to choose is this, 0 and V, but I'm going to put it at square root of 2 because I'm preparing for the standard model, and we parameterize it like this, and sorry, okay? Now I want to compute the mass spectrum, okay? And to compute the mass spectrum, I take the Lagrangian, right? And I replace the field in the kinetic term by the vacuum expectation value, and that should be the mass of the gauge bosons, right? The only quadratic term in the gauge bosons is the term in which the field is a constant, which is the vacuum expectation value, okay? So now, I do this in the following way. I have G square from the covariant derivative. Then I have the gauge field A mu, mu. Then I have 0 V over the square root of 2. This is because it's phi dagger here. And then I have TATB. And then 0 V over the square root of 2. And I leave it as an exercise to show what this is. But essentially, all you need to use is that the anti-commutator of TA and TB in SU2 is equal to delta AB divided by 2. Using this, then you get the answer, which is somewhere, which is that the masses are essentially, and so this is going to be G square V square divided by 8. You have to get that 8 from this 2, et cetera, times A mu, okay? And so this is the mass term for the gauge bosons. They all acquire the same mass, which is GV over 2. Okay, it's 1/2 m squared, so GV over 2, all of them, okay? So all of them, and so if you did that exercise before, where you broke SU2, and you realize all the generators are broken, that means all of the gauge bosons get masses, okay? All right. You can actually do the SU3 now for the same pattern of breaking of the SU3. And I'm going to ask, I'm not going to do it, how many gauge bosons will get masses in the SU3 example with the vacuum that actually we chose in the SU3 global case? How many gauge bosons will get masses? And so how many generators were not annihilated in the vacuum? Somebody did this, and I said, you're asking, and it's 5. There were 5 generators that were not annihilated in the vacuum, T4 all the way to, right? And then there's going to be 5 gauge bosons with mass. And there are going to be 3 remaining without a mass, which is the SU2 unbroken, okay? Now, in the remaining time, now, we're just going to use all of this to write down the standard model, okay? And then I'm going to have to rethink a little bit the rest of the lectures. I'll comment at the end. But tomorrow we'll start a little bit with some comments on SUSY, and I'm going to composite Higgs. And then at the end, I'm going to add some more things about the standard model that have to do with the baryogenesis that don't have to do with electroweak symmetry breaking necessarily, okay? Now, in the standard model, we know the electroweak standard model. Remember that the gauge symmetry was SU2 left cross U1 hypercharge, and we needed to break spontaneously, now we know, spontaneous symmetry breaking, to U1 electromagnetism, and that was it. That was what we needed, okay? So now we have the tools, and the question is, how do we come up with this? This is the closest we've gotten, but everybody gets a mass. That's not good. So how do we do this? Oh, well, we have the U1, so everybody gets a mass here, but not here, but this we know is not the electromagnetism. And so the point is that there's going to be a sum of generators. The generators here are the Pauli matrices divided by 2. The generator here is the hypercharge of whatever particle, in this case will be the Higgs, times the identity in 2 by 2. Every time I write some hypercharge, what I really mean is the hypercharge. Well, sometimes I won't, but sometimes it will be obvious that there has to be an identity matrix next to it. And so what's going to happen now is that now so basically, let's say that this is the theory now in the standard model. Then I need to add, the potential is the same, and I need to add oh, I don't know why I erased that. I need to add, see, these are the SU2 gauge bosons, just like I had before. And I have to have something which is the field strength of the U1 hypercharge. So this is the U1 hypercharge field strength, like we know we had before, right? Now the question is, now the Higgs field, which is a doublet field, okay? And now the question is, this is the vacuum I'm going to choose. I'm going to imagine, so the field itself, of course, has a lot of components. There is a component up here. There's a complex scalar field. There is a component down here. And I'm going to give them a name. Okay, this one is going to call phi plus, and this one I'm going to call phi 0. Okay, doesn't mean anything. I still don't know where the electromagnetism is, right? So these are names. So this is a complex scalar field. This is a complex scalar field in general, right? So there are 4 components here. Okay, but only the lower component is going to get, the real part of the lower component is going to get shifted by this VEV, vacuum expectation value. And then what I do, the covariant derivative on the scalar field now is going to be this one, IG times the SU2 fields, A mu times the SU2 generators, and then I have I G prime times the hypercharge of the field phi that I have to choose times the identity times the field phi. So this is the covariant derivative. Another question is, who is the hypercharge of this field? And I'm going to decide on the spot. The normalization of the hypercharge, this is a decision to be made. And based on that, all the hypercharges of all the fields in the standard model will come. And some people use 1, some people use 1/2. That's life, okay? I'm going to use 1/2 because these guys are Pauli matrices divided by 2, just like that, okay? But that's not, okay? So I'm going to choose that the hypercharge of the scalar is equal to plus 1/2, okay? And now, all I need to know is, look, I really want to go to the, this is, I know that there, here is the situation now in the breaking. What should be the generator? There are 4 generators in this product group, right? And one linear combination of generators, not each generator. So if I have any generator, right? This is the identity. If I apply any of these to the vacuum, I don't get 0. So it doesn't look good, right? Each of them, none of them will give me 0. But what happens is that there is a linear combination of generators that does annihilate the vacuum. And the linear combination that does annihilate the vacuum is T3 plus the hypercharge generator here. This linear combination times the identity applied to 0 whatever here, this gives me, this annihilates the vacuum. You can convince yourself if this is, 1/2, 0, 0, minus 1/2 is T3 plus, and then you have 1/2, 0, 0, 1/2, right? And so you get basically 1. And when you apply 1 to 0 v over equals 2, you get 0, okay? So this combination, the third component of the third generator of SU2 So essentially a linear combination of the diagonal generators of this product group annihilates the vacuum that I chose. And that has to be proportional to what operator in the standard model? That linear combination has to come with a linear combination of gauge bosons that will be what? What will be the mass of that gauge boson because, you know, this happens? 0. What's the name of that gauge boson? The photon. So if the photon comes attached to this operator, what's the name of this operator? The charge operator. Okay, so that's something we know, and now that's the electric charge operator, and that has to be the charge operator for any other particle with whatever hypercharge. That will allow us to fix the charges of all the particles that interact with this SU2 cross U1 gauge, okay, interaction. Now, what about the masses of the gauge bosons? The masses of the gauge bosons, which we've been doing here, for this, we are going to do the same thing now. With this vacuum, you can compute the masses of the gauge bosons, right? Masses of the gauge bosons here. All right. So we do the same thing to get the masses of the gauge bosons. And so what do we have? It comes from the covariant derivative of the vacuum expectation value, you know, written like this. Of course, there is no derivative of this. It's just the mass terms. But I write it like this. Okay, and so this is, you know, 1/2. Let me just write it like this: 0 v over the square root 2. Then we have g times a ta plus g prime times the hypercharge of the Higgs times b mu. Square, okay? So this is GAB TB plus G prime, the hypercharge of the scalar field B. This is mu up, 0 V over the square root 2. You do this calculation, and you get this. You get 1/2 of v squared divided by 4, and then you get g squared a1 mu plus g squared a2 mu plus, of course, g squared a3 mu. So it looks like these 3 gauge bosons from SU3 got the same mass. Right? But now, it turns out that now have plus minus twice g prime a3 mu times b mu. So they're mixed, okay? And finally, plus g prime square b mu. So there is a mixing. There is a mixing between A3 and B, and so I have to, you know, diagonalize that basis, and that's going to be the Z and the photon. That's good. But then we know that these guys are getting GV over 2 as their mass, right? And so I'm going to rewrite it like this. If I define W mu as A1 minus plus I A2, divided by the square root of 2, then I get that the charge masses are going to be G square V square over 4 divided by, times MW, times W plus mu W minus mu. Incidentally, nobody asked me how come the mass of the gauge bosons is positive in the Lagrangian. Nobody is bothered by this. We always said, look, the mass square needs to be negative in the Lagrangian, positive in the potential. So how come is this? So this is a question for you to think. How come the masses square of gauge bosons are positive and nobody finds this problem, whereas the masses of the scalars have to be negative in the Lagrangian, positive in the potential? Otherwise, I break symmetries. How come? Don't answer, or maybe if you know the answer. But okay, think about this for the discussion. Okay, so what happens with the neutral gauge bosons? Well, the neutral gauge bosons need to be diagonalized. And unfortunately, I'm running a little bit late, but the diagonalization is very, very simple. So we can do it very, very simply. For the neutral case, I'm going to take these three terms here, and I'm going to write them in a sort of a matrix form for you. So the L neutral mass terms, I'm going to write them as this, is 1/2 V squared divided by 4. And then I have this matrix form. I have A3 and B. And then I have this 2 by 2 matrix, which is G squared, G prime squared. And here I have minus G, G prime, minus G, G prime, times A3 and B. And so this should be exactly the same as these three terms. Right? We split the mixing term in these two. What's the determinant of this matrix? What's the determinant? 0. Which means that one of the eigenvalues, at least, has to be 0. Good. Because we need a 0 eigenvalue, which is a photon. Okay? So we diagonalize this, and we get that the photon field, which is the 0 eigenvalue, is some mixing of these two fields. So this is the 0 eigenvalue, prime, times G prime A3 plus GB. Okay, so this is the 0 eigenvalue. And then the other eigenvalue, which I'm going to call, the other field with a non-zero eigenvalue, same square root. And is the orthogonal combination G A3 minus G prime B. And that's the Z. And the mass of this eigenvalue is something, okay? And it's, in fact, G squared plus G prime squared divided by 2 times V squared, okay? You can do that just by diagonalizing these 2 by 2 matrix and just getting the eigenvalues, okay? So that's the photon and the Z. Now the next step would be to, instead of having so now we know what happens with the gauge bosons, right? Now the question is, so we have the 3 massive gauge bosons, 1 massless gauge boson. This is not a miracle, right? Again, this happens because I know that in here there is a combination of the T3 plus Y of phi that annihilates the vacuum. So there must be the reason why there is a 0 eigenvalue. It's not a miracle, okay? All right, good. And then finally, what we have to do, which we're not going to do now, is to couple these gauge bosons to matter, right? In a way that the photon couples the way we know. And so, whenever I couple it, then there's going to be T3 plus the hypercharge of some fermion. Well, this has to be the charge, right? So we know the charge of all the fermions in the standard model. And so we're going to fix the hypercharges just by getting the correct charge of all the fermions in the standard model. And that way we'll know all the hypercharges of the standard model. Okay, that's by hand. But then it turns out that there's going to be the couplings of the photons, of course, are fixed to be the correct couplings, but the couplings of the Z will be just predictions of the theory. And then we have to go and measure. And they're going to be absolutely crazy couplings, and I'm going to show you to you. And they're all measured with an incredible precision. So I'm going to stop right here. Maybe I still have a couple of minutes for questions, and then I'll just, yeah.
Thank you. So, there are urgent questions. Go ahead. Oh, sorry.
Okay. Of course, I understand that you have to diagonalize this kind of matrix because you have mixed terms. But can you remember me why we have to define the W plus and minus in that way? Because the AME1 and AME2 are, to me, they have mass terms.
At this point, I didn't tell you why.
Okay.
It turns out that this is suggested by the way the A1 and A2 will couple to fermions, and automatically you'll see that they'll couple as this combination always. And so we might as well do it. But it's easy to see that A1 and A2 coupling to fermion doublets, they have to be doublets because these are A1 and A2 are from the SU2L, only coupled to the left-handed fermions. When you couple them, you'll see that they couple with this combination, A1 minus I, A2 over times the fermion. And so naturally, you will see that the couplings are the W plus and W1 is coupling to fermions. So this comes naturally. Hopefully, I can put that in the notes, and maybe I'll show it. Okay?
Okay, great. Thank you.
Gustavo, maybe it's because that's the way they couple to the raising and lowering operators.
Right. So
and
the
so
doublets
increase the isospin of the fermion by 1/2.
Exactly. So one thing that we know of why is it that we put I don't know, the up quark here and the down quark here is that the difference between the up and the down, the top and the bottom or whatever, has to be 1 unit. There's isospin 1 and isospin minus 1/2. And so it has to be 1, the difference, right? And so if you're going to use, so in a way, this will be a consistent way of seeing it. But I can tell you that if you couple these to fermions, then inevitably the coupling to fermions, if you remember, you have the covariant derivative applied to a left-handed fermion. That means that there's going to be a minus IG, A1 and A2, T1 minus IG, T2. This sum, when you couple to the doublet, it'll be always giving you the coupling to each of the fermions on each side of the coupling. So you have a sidebar left here with an I, right? On each side, it will give you this combination or this combination because of the sigma 1 and sigma 2, right? And so if you write these metrics here, A1 T1 plus A2 T2, you'll have, A1 minus I A2 here and A1 plus I A2, and then 0 and 0, because you have to change the isospin. And then when you do this coupling, you see, well, this is the combination that couples to the up and the down. So inevitably, the symmetry tells you just use this one, because that's what we see experimentally.
Yeah, those are the combination that change an up into a down, or a down into an up.
Into an up, exactly. And so essentially, this is the only way they couple. So, but at this point, you're right. There's no reason why complicate things at this point. They're perfectly nice, but it is the fact that they couple this way.
Other questions, other comments? You have one? In the chat.
Okay.
Okay, let's see the chat a moment. So, Juan Garnica, this means that you always have to write a scalar field
No.
in the fundamental property if the generator manipulate the vacuum?
No.
No.
This is, as I said at some point, I think it's a physical choice. I could have written the theory for a scalar in the triplet representation, in the adjoint representation of SU2, get a vacuum expectation value, then the whole thing will work differently, and then I will just make experimental tests. One experimental test, for example, would be what is the ratio of mz divided by mw, square, something like that. In here, there is a combination of couplings that are different for the mass of the W and the mass of the Z that comes from the structure of that we chose. The representation of phi is crucial. Whereas I would get completely different mass ratios for Z and W if I use a triplet, for example, representation. And then I can go and measure the masses, and then I can see that this is completely wrong. So sure, I can choose the representation differently, but it would be experimentally excluded if I did the standard model this way. But in general, in quantum field theory, I can choose the representation of the fields as I see fit. And in this case, people wrote theories with the scalar in the triplet representation. Before, for example, the Georgia-Glashow model that I mentioned yesterday, that broke SU2 into U1, this doesn't work with the fundamental representation. This works with the scalar, with the Higgs in a triplet representation of SU2, and it has two massive charged particles and a photon, okay? And that model is completely excluded by experiment for various reasons, but it was a choice that Georgia and Glashow made. It's possible, at that time, before the discovery of neutral currents.
Yeah, related with this, I apologize for the comment I made before, because you break to the maximal subgroup, in fact, when you use the adjoint representation, not the fundamental.
With the adjoint.
So for the fundamental, the breaking to SU2 is certainly correct. Another question, that's not easy to answer. How we could check for spontaneous CP violation in generic scalar potentials? Is it similar or different? Because it is discrete.
So it is different because it is discrete. And I don't know exactly how can we check it. You mean experimentally, perhaps?
Also theoretically, I guess.
Theoretically, okay. It's a discrete symmetry broken spontaneously. I don't know what you have in mind in which spectrum, but maybe there is something in the spectrum.
Well, first of all, you don't have Goldstone bosons, no? Because it's discrete.
No. There are no Goldstone bosons, but there is something, maybe some coupling is different.
Well, you need some complex physical phase of some field that gets a web.
Right. So I don't know exactly. Depends on the model what will be the case. So you'll get CP violation, but in the end, I'm not sure. Depends on the model how you got it first. But yeah, it's possible to get to break discrete symmetry spontaneously.
Yeah.
But it's not. It depends on the model how you check it. I don't know.
Okay. Another question.
When you chose the unitary gauge, you got rid of the pi x field, right?
Yes, they Nabu Goldstone bosons.
Yes. So that's why we don't talk about the Navier-Stokes boson throughout your class, because it was we got rid of it. But there will be another scenario where those fields are important, not on symmetry breaking, but on other thing that we cannot get rid of the pi x.
Tomorrow. The answer is yes. If you break a global symmetry, let's just pick an example. Chiral symmetry in low energy QCD, you break, and then you get, if it's an exact global symmetry that you break, you should have, if it's SU2 chiral symmetry, or you break really spontaneously the axial symmetry, you get 3 Nambu-Goldstone bosons. Who are those 3?
The pions.
You can say it. They're the pions. So the pions are an example of the Nambu-Goldstone bosons in the spectrum. They're not massless because the symmetry, the global symmetry, wasn't exact. So we're going to talk about that tomorrow. Another possible example maybe is the Higgs, which is what composite Higgs bosons mostly today are, or nowadays are about. So we talk about tomorrow too. But if you break a gauge symmetry, the Nambu-Goldstone bosons are always going to be eaten or absorbed by the longitudinal component. So here, if I didn't go to the unitary gauge, I will still have these guys plus the massless. There will be 3 massless objects coming from here. These 2 real scalar fields in the complex phi plus the imaginary part of phi 0. These 3 are the Nambu-Goldstone bosons. And then those 3 are eaten by the W and the Z. Okay?
Thank you.
So they play a role, depends on the gauge you are.
So I suggest we stop here. Otherwise, we have to shorten too much the coffee break. But of course, in the afternoon, second half of the afternoon, you will have the discussion session where you can ask further questions or ask for further clarification. We reconvene, Rogerio, at 11. So we have 20 minutes. Thank you.